the previous lecture we were discussing about capacitance measurement using operation amplifier circuit. So, there we have discussed if we use a non-inverting amplifier, for example, if we have a op amp and then if we use a non-inverting amplifier for capacitance measurement, we connect the resistance here and then we had shown that we can put 3 plates, then we can have source here X and then another source which is V1 V2 and then we can connect to this. This is actually useful for space variation. Actually, if I have a space variation, then what was the output was coming, and then we also had shown that if we use the non-inverting amplifier again, I can also use for area variation. So, I can have this, then instead of these 2 sources are 180 degree out of phase, 180 degree out of phase. So, the same thing can be achieved with the use of transformer. You can have a center tap transformer which gives me more accurate 180 degree out of phase voltage. So, I can have 2 plates excited by this and the center plate can be connected to this amplifier. So, we can have this is grounded and then we can have other source connected to this. So, you will have a V1 and V2 and then we will have the output voltage here. This is the second method, that is low Z with space variation. This is high Z, low Z, this is again low Z, the low impedance, low Z with area variation. Then there is similarly there are 2 other methods, that is we can show same technique, that I can use it in the high impedance amplifier stage. So, I can use high impedance amplifier, then we can have same 2 techniques, that is we can have excitation voltage here and then the 2 voltages. For example, if it is a area variation, then we can connect the similar stuff here and then can connect to this amplifier. This amplifier, then you will get the output voltage. Same thing can be done with again this is we call Isit space variation. Same thing I can do similar stuff. You can have the same transformer, then we can have a space variation here, wherein this is connected here, and then 2 V1 V2 are connected here, V1 and V2, and then you get the output. This we call Isit, I impedance. The I is this is Isit area variation, Isit area variation. This Isit space variation. So, we will number them actually, because now we want to see in a consolidated manner what are these amplifiers, what are the disadvantage and advantage of each, and this we call number 1 and this we call number 2 and then we call this number 3, circuit number 3, and then we call this circuit number 4. Then we also can have 2 more variants possible in this, that is we can have Isit amplifier, then in Isit amplifier we want to make the output to be 0. So, what can be done is, for example, if it is a space variation, I can have the excitation voltage given here, and then this is given to high input impedance terminal, and then this can be amplified. This can be amplified, and then this can be summed with the error output can be summed with the feedback. This can be done. We had seen this earlier actually. This earlier last class we had seen that is the same circuit as that of with the feedback, the high impedance amplifier with the feedback, the same circuit which now we are calling as circuit number 5. We call this a circuit number 5. This is actually Isit amplifier with space variation with feedback. Same thing possible in another variant is the 6th circuit, wherein we will have Isit amplifier with feedback, Isit amplifier with the feedback. So, we will have it's the area variation. We can have 2 plates and connected to this one, and one can be excited with the source of V1, the other one can be from feedback. So, we can have this amplify the signal, then we can have the summing amplifier connected here. This can be connected to input, and this actually connected to this. So, this we call circuit number 6. Circuit number 6. This is Isit amplifier with area variation. With feedback. So, we have 6 different possible circuits for this capacitance measurement. So, we have to see each one of it where to use, and then which is better for a given application. So, we have picked up basically 2 different applications, one is area variation, another one is a space variation. And then we have taken 2 different amplifiers, one is non-inverting amplifier, other one is a inverting amplifier. So, non-inverting amplifier gives you high impedance input. So, we call Isit amplifier, and the inverting amplifier gives you low impedance. So, we call it is a low impedance low Isit amplifier. And then in the case of high impedance amplifier, we can also have a feedback, and then one can make the output to 0. So, same thing also possible with the low Isit amplifier, which will make another 2 more circuits, that is 8 variants really possible actually. Now, we will see about the other 2 circuits afterwards, that is low Isit amplifier with the feedback, what is the effect that it comes, because it may not be required in the real application. Because if we take the low Isit amplifier, that is our circuit number 1, if we take this is actually we are calling low impedance because we are giving it to the non-inverting input. So, this is at a ground potential, because this is since this is at ground potential, this is also ground potential, we call this a low Isit amplifier. And in the case of circuit 3 and the other 3, 4, 5, 6, we are given the input to the non-inverting amplifier. So, this offers high impedance. So, this we call it is a high impedance amplifier. Now, if we take the low Z with the space variation, we had shown in the previous class that low Z with the space variation, we will have a output voltage that what is coming here, these resistance R. So, the current actually is delivered by this and the current delivered by this. If these two are from V1, V2 are from the same transformer, then they are identical voltages, but their 180 degree out of space can be there. Now, this we can actually modify like this, that is I can remove this, and connect the transformer, center tap transformer. So, one is energizing one plate, another one is energizing the other plate. So, this is AC that it is coming here. Now, in this case the output, that is output voltage is actually given by, suppose we take this one C1 and this is V1 and this also V1 and this is C2. So, we had shown in the previous class that what is the output voltage. It was shown that output is not linear with the displacement D, because we had shown that if the D is a displacement, output is not linear, the output voltage output is not linear with D. So, this is not a linear circuit, and then but of course, it has advantage that there is no effect due to the stray capacitance, because the stray capacitance has no effect, but this is 0 potential, this is also 0 potential. So, it works very well, no problem, but unfortunately output is not linear, and then output voltage is not 0, and output voltage depends on frequency as well as input voltage variation. Where the frequency changes, then you will find that output voltage also changing, and then even if the voltage changes, the output voltage also changing. So, this is not as good as ratio transfer bridge that we had discussed earlier. Now, the same amplifier, if I take low Z with area variation, this circuit is linear, V0 is linear with area with displacement, because we are moving the core like this. I think we have not shown this equation in the last class. Let me see what we had done in the previous class, whether it was derived or not. Area variation we had shown. So, output voltage is linear, this we had shown in the previous class. This linear or non-linear, that is what we had got a question. In the previous class we had shown that this circuit, that is number 2, low Z with area variation, V0 is displacement is linear, and we had shown the equation derivation also. So, this has advantage because output voltage is linear with the displacement. Of course, it is again depends upon frequency variation, because if the frequency of the source varies, then output voltage also changes, and even if the voltage varies, then output voltage also changes. Nevertheless, it is linear, but it is not comparable with the ratio transformer bridge. Then we had shown other circuit, that is our number 5th circuit, which is actually feedback, because we want to use feedback and then design a circuit using a non-inverting input, because we are fed to the non-inverting input the signal, and then this output voltage whatever is come that we are amplified, and then we invert it and giving back to the other plate. In this method, we had shown in the previous class that this derivation also was made in the previous class. We had shown that with this one, this is not linear, and this is not linear because we had shown that C1 plus C2 if we take because if we take this circuit number 5 and 6 which are actually with feedback. So, essentially our aim is that we want to make this voltage as small as possible, because if the gain is large, if the gain is G is large, then the error voltage will be very small and this voltage will be very small. So, that is what our discussion, the aim is that if we have a stray capacitance here or the cable capacitance, that should not have any effect, means the input voltage should be 0. That is the basis of circuit 5 and 6. So, here also we assume that the capacitance is there and this voltage is very small, and so the output voltage will have no effect on the stray capacitance. So, if we take circuit 6 and 6, 5 and 6, circuit 5 and circuit 6, feedback keeps the non-inverting input of the first amplifier near to ground potential. This makes the stray capacitance are ineffective. So, this is that is the advantage, because the input capacitors have no effect. So, because of we are feeding the signal back and then making the input at the input signal is 0. It is happening in both circuit 5 and 6. In both circuit 5 and 6, if as long as the gain is high, the input voltage will be very small. So, the stray capacitance will have no effect. But then if you analyze the circuit, whether they are linear or non-linear. So, we had seen for example, for the space variation as well as this is for space variation. So, for space variation if we take, so we have to take here if take D and the plate moves, then one side becomes T minus x and the plate comes down, this distance becomes T plus x. So, this distance and this distance varies in the case of space variation. And the current actually, since these two voltages are 180 degree out of phase. So, the current at 0, when assuming that V input is 0, if V in is nearly 0, then we can show that V1 C1 omega should be equal to V2 C2 omega. So, where C1 is this capacitance, C2 is this capacitance. There have to be equal, because then only then this current is actually V1 C1 omega, and then the current coming from here is V2 C2 omega, and for 0 they have to be equal. So, that actually makes the equation simple. So, we can write that V1 by V2 is actually C2 by C1. But then if we write in terms of D, that C we can write it as C1 C2 minus C1, we can write it as that's C2 will be A by D plus x, D minus x in this case, it will be D minus C2 is this capacitor. So, we have taken as D minus x, then divided by A by D plus x. A also goes off. So, eventually this will be simplified as d plus x by d minus x. So, that is the voltage V 1 minus V 2 will come, which shows that the volt is clearly nonlinear circuit, and apart from removing the stray capacitor effect, the circuit is not advantageous even for space variation measurement. Similarly, if we take the other circuit, that is 6, that is wherein we are using Isit amplifier and then giving the feedback such that this voltage becoming more nearly 0 by giving a high gain. But again this is for area variation, because we are moving the plate, the 3, this is area variation. So, by moving the plate 3, we are varying the area increasing. So, assume that this is having A into 1 minus x area, and this actually plate area increases, we take A into 1 plus x as this area. So, if you again write the equation for the current. So, one current will be V 1 C 1 omega, that is if I take this as C 1 capacitor and this as C 2 capacitor, then V 1 C 1 omega will be equal to V 2 C 2 omega. So, again we will get up V 1 by V 2 as C 1 by C 2 by C 1. Then C 2 can be written in terms of area, that actually will come. So, C 2 will be A into 1 plus x, here it will be A into 1 minus x, other parameters actually goes off. But again you find that this is again nonlinear, that is V 1 V 2 is nonlinear with the displacement. But interestingly, this does not depend upon the dielectric constant variation and the frequency variation. This is true for circuit number 5 also. Circuit number 5 again is independent of dielectric constant variation and the frequency variation. Of course, it is nonlinear, otherwise the circuit is excellent proposition, because we can give the feedback around and make it make the input bring the input to the near to 0 potential. So, we will not have any problem due to the stray capacitance. Nevertheless, the circuit 5 and 6 actually become actually a nonlinear circuit, and in some applications it can create a problem, because at the extreme ends the signal strength might come down, other than doing a computation using probably today it can be done easily with microcontrollers. So, if we see this, out of these 6 circuits, that 5 and 6 even though the input is 0, we are using non-inverting amplifier, they are not effectively good, because they are nonlinear. And then if we look at circuit 3 and 4, that is let us not make the output 0, but we will not give a feedback, but we see what effect we will get if I use Isit amplifier for area variation, that is the circuit 3 we use, what happens. And then if I use the circuit 4, again circuit 4 is for this is for space variation, this is for area variation. In this case what advantage we get? Obviously, if the output is not 0, we can see one disadvantage, that this is also not 0, input also not 0. So, same thing, if this is not 0, the input also not going to be 0. That can create problem, because you will have a stray capacitance here to ground, and you can also have a stray capacitance here to ground. So, stray capacitance will have severe effect on the signal. So, these two circuits we analyze little more in detail separately now. So, let us get into the these two circuits for detailed analysis. Now, let us take this transformer secondary, and then I connect the input here, that is a AC. Then I will use first we will take Iz for space variation. So, space variation I will put the 3 plates, then I connect one of them here, and that is the output voltage. If need, gain also can be given. So, I can connect one of them here and another one here. So, we will have this is actually V1, V2 and then C2, C1 can be taken and the output is 0. Assume there is no stray capacitance effect as a assumption first. So, one assumption is assuming no stray capacitance present here, that is this is 0, no stray capacitance at the input of the op amp. So, we will analyze assuming there is no effect due to this, and similarly V1 second assumption is assuming V1 equal to V2, V1 equal to V2 and 180 degree, and they are 180 degree out of phase, because this is anyway transformer that actually 180 degree out of phase automatically happens. So, there is no problem with that. If this assumption is made, then we can show that the input current that is coming from here, that actually goes here, and the input current that is coming here goes here. Now, if I want, since there is not 0, so we cannot take the currents as it is. So, we have to analyze in terms of voltage. So, we can write what is the output voltage in terms of C1 and C2, that is what we have to write now. So, if we take that, then the equivalent circuit becomes like this, that I have two capacitors, one is with V1, another one is with minus V1, and then here is the voltage V0, that is C2 and C1, that is C2, that is C1. So, we have to find out what is the voltage V0. Now, we can write using superposition theorem what is the value of V1. So, contribution due to source 1, I take this as a source 1, that is a source 2. So, using superposition theorem one can find the value of V0 using superposition theorem. We can find the V0 can be calculated. So, that is actually V1 into ZC2 divided by ZC1 plus ZC2, that is the contribution due to V1 by connecting V2 to ground, source 2 to ground, source 2 to ground. So, where ZC2 is the impedance of capacitance 2 and ZC1 is impedance of capacitor 1. So, ZC2 is nothing but impedance of capacitor, ZC2 is impedance of the capacitance C2. ZC1 is the impedance of cap C1. Similarly, we can find the contribution due to source 2. So, second part is contribution due to source 2. Contribution due to source 2. Here actually we will get the contribution due to source 2 as V1 is the excitation voltage V1 into ZC1 divided by ZC1 plus ZC2. So, adding these two will get the net voltage V0. So, adding 1 and 2, this is done by grounding source grounding source 1. So, adding 1 and 2. So, this is the equation 2 and then we had the equation 1. So, adding 1 and 2 we can get the output voltage V 0. So, V 0 actually become, so V 1 into ZC2 divided by ZC1 plus ZC2. Then since other one is minus, I can actually we have to add, since the polarity is reversed, I can write it as V 1 into ZC1 divided by ZC1 plus ZC2. So, that is the equation that we get for output. Its output obviously not 0. Now, the question is whether it is linear or not, because this is space variation. You will show that it is actually linear, because even though this is a disadvantage that it is sensitive for input capacitance, nevertheless this is gives you linear output. That is the advantage of this circuit. Now, that we can show like this, since V 1 now it can be simplified, V 0 can be shown as V 1 divided by ZC1 plus ZC2, and then we can show ZC2 minus ZC1. Now, if we write ZC1 is coming as j omega A by d plus x, I can write, and ZC2 can be written as j omega A by d minus x. And of course, mu naught epsilon naught epsilon r also there, that one need not worry about that, because that anyway will be we will show that it is getting cancelled. Now, if I simplify ZC2 C1 minus ZC2 minus ZC1 divided by ZC1 plus ZC2, that is coming as we can show that that will be C2 minus C1, that will come 1 plus d minus x minus 1 by t plus x divided by 1 by d minus x plus 1 by d plus x. That is what the term comes out. So, that actually if we simplify this, then you will get the bottom terms are actually constant. So, you will show that it will come as d plus x minus d minus x divided by d plus x plus d minus x, because the if we can take a common factor, that it goes off. So, you will get the net result as this. Now, if we simplify this, that comes out as 2x divided by 2d, that comes as x by d. That is ZC2 minus ZC1 divided by ZC1 plus ZC2. So, then V0 will become, because V0 is shown as this. So, V0 will be V1, V0 will be V1 into x by t, which is actually linear, because d is fixed, V1 is fixed, So, V0 is proportional to x. So, it is linear. So, even though this amplifier is not good in terms of stray capacitance effect, this is good because it is linear. So, that is the reason that this amplifier also popular. Now, the dependence of this capacitance can be solved by giving guarding the input. So, normally what is done is to solve the input impedance stray capacitance problem, one can guard the input electrodes. So, using the following technique, that is we can have the input and then the two space variation. So, we will have and this input can be used ground capacitance and can be connected to this. This partly nullifies the input capacitance problem, but not completely, but nevertheless it is linear for displacement D. So, this is that is why it is very popular, because the non-inverting amplifier was linear for area variation, whereas this non-inverting amplifier is linear for displacement T, and then this inverting, that is low Isit amplifier is linear for space variation. That is, if you recollect the circuit, that is this. So, we have the output voltage here and then the same center tap transformer. We have to go for area variation. So, we have the two plates and then that is connected to this, and then one is actually connected to this plate, another voltage is connected to this. So, again this is also linear for space variation, low is linear for area variation, sorry, this is for area variation. So, linear for displacement D, and then this is linear for area variation. So, these two amplifiers are actually used in real life, so that you get a linear output for the given displacement, or that is in the sense that by using area variation one can measure the displacement. Here you can using the space variation you can measure the displacement. Nevertheless, this amplifier is good in terms of stray capacitance effect. This is not very good in terms of stray capacitance effect. Now, that what is remaining is the circuit number 6. What is the effect of circuit number 6? Now, circuit number 6 is actually sorry, circuit number 4. Circuit number 6 we already discussed. Circuit number 4, if you see here actually Isit amplifier for space variation. So, how this amplifier behaves we can see now. So, we take this Isit amplifier for space variation. Isit amplifier for space variation. Here actually we have the input Isit amplifier for space variation. So, we can have this, and then input is energized with this, with the center tap transformer. So, we have space variation we have to bring in here. So, we will have the 3 electrodes here. Of course, again we will have to put a guarding technique here to avoid the stray capacitance problem. That is coming as V1, V0, and then V1, that is V1, and then we will have C1 here and C2 here. Now, this also can be analyzed in the same form, and then we can show that it is also not linear, because we can write the same voltage equation by using a superposition theorem, and then if you look at the superposition theorem equation what you have written. So, we will get V1 into ZC1 divided by ZC1 plus ZC2 plus that is inverted. So, we have to have a minus voltage. So, you will have minus Z V1 ZC2 divided by ZC1 plus ZC2 we will get. Now, it is similar to what we had, but except that ZC1 C2 that is a V naught. Now, we can show that this is also nonlinear. For example, ZC1 C2 ZC1 will come as, here it is a space variation. So, you will have a constant and you will have 1 is t plus x, and ZC2 ZC1 will come in terms of this constant k is there, and ZC2 will be a by d minus x into the constant k, which is actually consists of mu naught, epsilon naught and epsilon r. So, that at this point of time we keep it as constant. Then if you find out ZC1 plus ZC2, that comes as a by d plus x plus a by d minus x, and then ZC1 minus ZC2, ZC1 minus ZC2 comes as a by d plus x minus a by d minus x. So, we can if again we write by ZC1 by ZC1 minus ZC2 divided by ZC1 plus ZC2, we write that actually turns out the a goes off. So, you will have at the as a upper term 1 by t plus x minus 1 by d minus x divided by you will have 1 by d plus x plus 1 by d minus x. That is what it turns out. That is the effect of this one. Then only then we have to take V1 factor to get into V naught. So, if you simplify this, you will get similar terms. Actually, we had a in the previous term, that is in the previous equation we had a plus 1 plus x and a minus 1 minus x we had. Okay, here also we come into space. So, we had written as due to this. Okay, here we are written as space variation. So, we have to take this as a area variation. So, there is a small correction. So, what I do is that the second equation I take it as a area variation, not as a space variation. So, this is anyway linear. So, if I had to take area variation here, though I had taken as Isit amplifier for linear for displacement d, this is for space variation, this is for area variation. Then Isit amplifier for space variation, we are already done this. This is already done. This is already done. So, we take next area variation. So, if it is area variation, then we have to take it as a into 1 plus x into a minus 1 minus x. Isit space variation was already done. Isit Isit actually space variation was already done. I will do now Isit for area variation. It is already done. So, Isit for area variation I do it, Isit for area variation. Here actually we will have the source we can have two voltages V1, V2. So, we will have so we can again we will have our guarding technique. So, if we write the same voltage equation for this point, we will get V2 into we take it as C2 and this is C1, V Z sorry V2 into ZC2 ZC1 divided by ZC1 plus ZC2 plus that is other contribution due to the other source, that we take it as V1 into ZC2 divided by ZC1 plus ZC2 that is equal to V0. So, now we can find ZC1 and ZC2. So, ZC1 actually comes out to be we had tried for suitable for area variation. So, that comes as A into 1 plus x divided by d, and then ZC2 will come as A into 1 minus x divided by d. So, that if you simplify, so that comes ZC1 minus ZC2, that will turn out to be A actually by d is common. So, you will have 1 plus x minus of 1 minus x, and then ZC1 plus ZC2 will turn out to be A by d is constant, then you will have 1 plus x plus 1 minus x. So, we can find now ZC1 minus ZC2 divided by ZC1 plus ZC2 will turn out to be 1 plus x minus 1 and plus x, and then the bottom one turned out to be 1 plus x plus 1 minus x, that turns out to be 2x by 2, that comes as x actually. So, ZC1 and ZC2 comes as x. So, that will give that output voltage V as if V1 is equal to V2, V1 is equal to V2, then V0 will come V into actually x. It is again it is linear actually. So, I set for area variation is turns out to be again linear. I set for space variation for space variation it is a linear. So, now we are seeing all the 6 circuits how each one is behaving for displacement. So, I set for area variation turns out to be linear. Now, we can select a circuit which is actually suitable for a given application. Of course, when the output voltage is not 0, we have to worry about the stray capacitance problem. So, these 6 circuits can be selected for any particular application. Now, one may wonder that why the feedback is not given for low Isit amplifier and made the output 0. One can try that also. So, that will give you 8 different circuits, and that is to be analyzed in a systematic manner. Now, let us turn into another application, that is how to make a water level measurement using capacitance sensor. Now, this is a technique that is used to measure the overhead tank, the level of the water. So, what is done is you have this and then put the two plates, one plate like this, then another plate in a inverted manner, then another sense plate which is in between these two, which is pasted outside the tank actually, and then this is connected directly to the amplifier. So, the amplifier is done like this, that is you have a amplifier, then this is actually we have a ground here. Now, the output minus, now this is connected to this, then sense amplifier is connected to this and this is connected to the source. Now, this output now depends upon the water level, and it is a wonderful circuit which has a very less effect due to the stray capacitance and so on. Now, if water is there, essentially we have a capacitance formed from here to water and water to air, and then from here to water, and then to the sense electrode. This is sense electrode, this is a source electrode, this is feedback electrode. Now, if you draw the equivalent circuit of this, that turns out to be like this, that we have a source. The source is connected to the input through two capacitances, that is we have one capacitor, that is a CS, and then C electrode and C feedback. So, we have CS and CE coming in series to this, and the feedback capacitor comes like this, and then we can also have we may also have leakage current to the ground from the water. So, that can be shown like this. So, the equivalent circuit for this turns out to be CS here, and then this is CF and then CE. Now, but we know that this is ground potential, this is also 0. So, one can assume that this also 0 potential, because when this is 0, there is no current flowing here. So, this also has to be 0 only. So, that is this we call point A. So, point A is at 0 potential. That is the crux of the controller here. In that case, this is because my negative terminal is at 0 potential, is at 0 potential, and no current through CE. So, we can now draw the equivalent circuit as like this, that is I can have a circuit like this and then have this. So, if this is 0 potential, I can ignore this and as well this, because there is no current through this. So, all these three parts can be ignored. So, the equivalent circuit becomes simply the two capacitors. And both of them depend upon this is CF and that is CS. Both CS and CF depend on the water level. Both CF and CS depend on the water level. The plates are inverted. The plates are inverted. So, with the water level, output V0 varies, such as this V0 varies. So, this is a wonderful circuit wherein the stray effects are actually removed. So, we are seeing now different circuits per capacitance measurement. Essentially, there are 8 different combinations possible, but it is better to use inverting amplifier configuration. So, the stray capacitor effect is not there. So, of course, the best circuit one can think of for capacitor measurement would be ratio transformer bridge. So, the best circuit is ratio transformer technique. But then this cannot be used in today's world, because one need to have a manual balance, but op-amp circuit, op-amp with non-inverting amplifier, inverting amplifier is the alternate option. Inverting amplifier is best, next best. So, with this I will stop the capacitance measurement technique. In the next class we will see A to D converter and D to A converter construction, and then usage details in detail. Thank you.